Well, all right, everybody. Great to see you all here. Can you guys believe this is our very last lecture of the whole year? I don't know about you guys, but it just seems to have like absolutely flown by. It just seems like a moment ago. You know, we were over in the sports centre doing that very first lecture. How's everybody doing? I mean, we're kind of coming to the end of the year. How are people feeling? You guys doing all right? Or okay, all right. So for the very last lecture that we're going to be thinking about, we're going to be combining a lot of the topics that we've been thinking about over the past few weeks. So we started, thinking about circular motion, and then we were thinking about Newton's laws of gravity. And today we're going to see my favorite example of combining both of these, how they both work together, by thinking about the physics of orbits. Now, this is my personal favorite topic in the syllabus. Lots of really fascinating physics, lots of really exciting stuff going on. So I hope you guys are going to really enjoy this one, finish on a good lecture here. Now, how many of you have studied orbits before? Okay, not too many people. Okay, all right. Now, the interesting thing about orbits is, oh wow, there are heaps and heaps of misconceptions when it comes to orbits. So what I'd like to do for the first question today, I'd like to poll you guys, but what I'd like to do is get a sense of, where's the thing? It's not going. There we go. Okay. To get a sense of which of these misconceptions about orbits have you heard before. So maybe you've studied orbits before, maybe you've been to like a space museum, you've heard some stuff. There's heaps and heaps of misconceptions going on when it comes to orbits. So have a think about these. Maybe they've been phrased slightly differently. So have a think about these. I'm really curious, how many of these misconceptions about orbits has everybody heard before? Usually, I'm always saying, don't worry too much about getting the right or wrong answer. The important thing is to engage with the question, give it a go, especially so for this question, because they're all the wrong answer. Okay, I'm not too worried about getting the right or wrong answer. I'm just really curious to see how many of these misconceptions have you guys heard before, and actually especially where you have heard those misconceptions, because I always think that's quite interesting. Okay, let's take a look. I'm really curious, which of these misconceptions has everybody heard before? Okay, so no one's heard misconception C and D before. Okay, so lots of people have heard no gravity in space misconception. Where have people heard no gravity in space before? Just kind of generally? Yeah, so I kind of pretty much guarantee any day of the week, if you visit like a science museum or a space center, there's going to be some parent there and they're going to be telling their kids, there's no gravity in space. And I guess you might even hear that, mentioned, in schools and things like that. Very, very common misconception that there's no gravity in space. And quite often this is how people think, what's going on, with space and orbits, that, we've got Earth and there's gravity, and you go up and there's space and there's no air in space and there's also no gravity in space, and, you just float around and it's all very fun. Okay, so some people heard space is very high, very far away. Who's heard this misconception? Okay, and is this to like explain what's going on with orbits and gravity and stuff, that you just have to get really high, really far away? Very, very common misconception when it comes to gravity. You might also hear people saying, in space, you're outside the gravitational pull of the Earth. So we're going to unpack that misconception a bit as well. And we're going to see, space, not so far away, and it's really not such an important thing when it comes to understanding orbits. Okay, so nobody's heard this one, the microgravity environment. Okay, now I bet if you listen out for this, next time you watch anything on the news about astronauts or the International Space Station or anything like that, I guarantee you the news reporter is going to say something about they're in space and they're in a microgravity environment. And this is kind of often used to explain what's going on with space, what's going on with orbits. The idea is you're in space and maybe, okay, we know that there's there is some gravity in space, but maybe it's, it's a million times less than it is on Earth. So we call that a microgravity environment. Now, this is kind of in some sense true, but generally not how people mean it. So very often you might hear people talking about a microgravity environment when they know that there is gravity in space, but they don't want to say zero gravity, so they say microgravity. And it does sound very sciencey and technical as well. So have a listen out for that one next time you see anything on TV about astronauts. Okay. Now, so nobody's heard this misconception. Gravity is cancelled out by the centrifugal force. That is a big relief of mine, because this is a very common misconception when people start studying orbits. If you go and you're revising orbits, reading stuff online, you may very well read this kind of stuff, people writing this, explaining orbits. If you're reading physics forums, that kind of stuff, there'll almost certainly be someone there explaining to you that, gravity and it's cancelled out by the centrifugal force, and the math kind of works, but it's not what's going on at all. So I'm glad nobody has heard that misconception as well. Hopefully we can just steer clear of that one. So I always think it's interesting to kind of get a sense of the misconceptions that people have when they are thinking about orbits. So let's start to have a think about, what's actually going on when we're thinking about orbits. And to do that, we need to start with Newton's law of gravity. So, we saw last time, the force of gravity between two masses. So let's start in this question. Given this force, what's going to be the acceleration due to gravity of one of our masses? Now, we've seen acceleration due to gravity loads and loads of times before, all throughout the year. Whenever we see that, 9.81 meters per second squared, the little g, the acceleration due to gravity. So we've been working with this a lot throughout the year. But what we're thinking about today is, how do we actually get this from the equation? So have a think, given this is our force, how are we going to work out what the acceleration associated with it? Just a hint, think about Newton's second law of motion. Force is equal to mass times acceleration. We know force is always equal to mass times acceleration. We have the force, have a think about what our acceleration is going to be. All right then, good to see those responses come in. Let's have a look. What's our acceleration due to gravity given this force there? Hopefully fairly straightforward. Okay, fantastic, 100%. Good place to start, okay? So, our force is gmm over r squared, and then that's equal to mass times acceleration. We divide out the masses, and then we get option B here, okay? So very well done, everybody, with that question. Hopefully not too tricky to start with, okay? Now, this is actually where, if you like, you can calculate that little g, the acceleration due to gravity. So this m is the mass of the Earth, this r is the radius of the Earth, and this g is Newton's gravitational constant. So if you like, you can give that a go. Hopefully you should get, 9.81 meters per second squared. Now, let's see how this is going to change if we are up in a orbit. Now, the only thing that's going to change is our distance. The planet Earth isn't going to get heavier or lighter. So let's have a think about this. On the International Space Station, the Newton's gravitational constant is the same, mass of the Earth is the same. The only thing that it changes from at ground level is that our radius goes from the original radius of the Earth, and then we're some additional distance away from the Earth. So this is the altitude above the surface of the Earth that the ISS is orbiting. So we just have to add those to get the total radius. So give this question a go. See what you get for the acceleration due to gravity when we're up on the International Space Station. All right then, well, let's take a look at what everybody thinks for this one. Let's have a look at the poll results here. Okay, so we've got a range of options here. Looks like most people are going for option D. Okay, so let's take a look at what we've got here. So we know that the acceleration due to gravity, so it's gm over r squared. So g, that's just the constant that we have here. M, that's the mass of the Earth. And r is our distance from the center of mass of whatever it is, so the center of mass of the Earth. Now, right now, all of us, we're on the surface of the Earth. So our distance from the surface of the Earth is the radius of the Earth, this 6.37 times 10 to the 6 meters. But if you want to be in orbit, you have to get above the atmosphere. So the International Space Station, it's about 400 kilometers above the surface of the Earth. So we have to add on this extra bit, okay, because the International Space Station, it is a bit further away from the center of mass of the Earth than we are right now. But the thing I want to emphasize is that in space, we're not actually very much further away. So right now we're 6.37 times 10 to the 6 meters, and we're just an extra 0.41 further away when we're up in orbit. So really not very much further away. But when you add that extra distance, what you actually get for the acceleration due to gravity up in space in the International Space Station, it's actually option C over here, this 8.82 meters per second. Oh, they should all be meters per second squared. It should all be meters per second squared. Sorry, I just noticed that. So that's the value that we get for the acceleration due to gravity, okay? If you did get that it's the 9.81 meters per second squared, just remember we've got to add on this extra bit, okay? Because this is the value that we get if we just think about the radius of the Earth, and we have to add on this extra little bit, okay? So this is the acceleration due to gravity in the International Space Station. Is anybody a bit surprised by this? What does anybody reckon by this? Is this kind of higher or lower than you'd expect? You reckon it's higher than you'd expect? How so? Right, you think it'd be much weaker, right? I mean, we've all seen, like pictures of astronauts, and it doesn't look like gravity's a little bit weak. It looks like there's no gravity at all, right? So if we have a look for a comparison, this is the acceleration due to gravity on the surface of the Earth, 9.81, and then in orbit, it's about kind of 90% of the value on Earth. So, it's really not very much lower at all. So when you hear people talking about a microgravity environment, maybe gravity is way, way lower, it's really not that much lower. So if you could build a tower, 400 kilometers tall, you'd be able to just kind of walk about on it. You probably wouldn't even notice that there's much of a difference in the strength of gravity. So this can be quite kind of surprising, right? We might expect gravity to be much, much lower. But, in reality, it's nearly as strong as it is on the Earth. And in fact, this acceleration due to gravity, it's much higher than it is on the moon. And, astronauts are sort of walking around there. So the secret to orbits, it's not about the absolute value of how strong the acceleration due to gravity is. To understand what's going on with orbits, we need to understand really the difference between mass and weight. So I've got this question here. We're thinking about how these concepts are going to be different in space. Now, we have seen mass and weight before last semester. This might be a good one to have a chat with the people around you, have a think about what's going to be the same in space, what's going to be the different, and the difference between these two concepts. Okay, so have a think about this question. We'll take a look at the results in just a moment. All right, very good. See those responses come in. Let's take a look. Let's see what everybody thinks for this one. What's the same? What's going to be the difference? Okay, so no one's going for A and C. Looks like most people going for option D. So remember, our mass, that's the intrinsic property, how many kilograms we have, okay? Now, in everyday language, we often use these synonymously, if you talk about losing mass or weight or all that kind of stuff. But, in physics, there's this difference, okay? So mass is our intrinsic property that we measure in kilograms, and weight is the force that we feel due to gravity, okay, that we measure in newtons. So, in physics, mass, that's kilograms, weight is the force of gravity the force of gravity that we measure in newtons, okay? So it looks like, as most people got, when we go into space, our mass isn't going to change, but what is going to change is the force of gravity. So the correct option is answer D. So very well done, everybody, with that question. And this is actually the key to start thinking about what's going on with orbits and why it looks like it's kind of zero gravity, even though the acceleration due to gravity is about 90% as strong as it is right now. because our mass is the same, but what has changed is the effective weight that we have. So let's see how this works with an example. Has anybody seen this example before? That maybe we're trapped in some imaginary cosmic elevator here in deep space. Has anybody seen this before as a bit of an example? Okay, all right. So the situation is that you're trapped in a lift and there's no windows, you can't see what's going on, and the lift is in deep, deep space, far away from any planets or anything. So we really can kind of consider this as a zero gravity environment. There's no planets, there's no stars, there's nothing else. It's just an empty universe outside the lift. And in that case, you really would be able to just float around really nicely. If you had some staff, it would just float around there and it wouldn't fall. We can kind of get this effect temporarily in Earth if we are also in the lift, but the lift is falling, okay? So if we're in a state of free fall, if we're trapped in this lift, so the lift is accelerating towards the ground, okay, with some acceleration g, but so are we. So we're accelerating towards the ground, but the floor of the lift, the ceiling of the lift, everything in the lift is also accelerating. So even though we're all being acted on by the force of gravity, all the stuff that we're looking at, that's also accelerating with exactly the same rate. And that acceleration due to gravity is going to be the same for everything. So for us, falling in the lift, because everything's falling at exactly the same rate around us, it's going to feel like zero gravity, okay? And this is really the situation that's going on when we are in orbits. Has anybody been in a kind of roller coaster or like a drop tower ride? When you just get winched up and then drops and you fall down? Has anybody been in those kind of? Which one did you go on?
I went on one in Germany.
Oh, okay. Was it a roller coaster or like a lift drop? Okay, okay. And I mean, you can do the thing, when you flick like a little penny or something and it falls next to you.
I think I've seen a video of it.
Okay, okay. Has anybody else been on like a ride like this before? Okay, which one were you on? Tower. Okay, okay. Did you like it? Okay, cool. So that's what it feels like to be in zero gravity. Now, clearly, if you're in a falling lift, you're not going to get zero gravity for very long. It might just be a kind of couple of seconds at the most before you hit the ground, and then your zero gravity experience is going to be over. So we have to think about what's going on in orbits. Now, you can get slightly more zero gravity if you're in a situation like this. So this looks like, it looks a bit like it could be in a space station or something, people floating around doing some experiments. Does anybody know where this picture's taken? What's the situation going on here? So this is actually taken inside an aircraft, so inside an Airbus. And what this Airbus does is it flies on what's called a parabolic trajectory. So it just flies up and then flies straight back down. And while the aircraft is flying in this parabola, everything is in a state of free fall, exactly like in that falling lift. So like in the Tower of Terror or those roller coasters where you're just falling. Everything in the aircraft, the passengers and all the experiments, is just falling at the same rate. So you can get slightly longer periods of zero gravity. I'm always curious, who would be up for going on a zero-G flight like this? Oh, okay, quite a lot of people, just for the fun of it, experiencing the zero gravity. Yeah, so it does look quite fun. And again, exactly the same sense of zero gravity that you'd get in an orbit. But of course this, I think you can get about a maximum of like 40 seconds of zero gravity. So if we want to keep going in zero gravity indefinitely, Isaac Newton actually figured out how we can do this. And it's really by this idea of just extending this free fall. So this is a wonderful illustration from his text from 1728, where he really figured out what's going on here. So the situation is, he imagined being on top of a mountain and firing cannonballs off the mountain, but firing them sideways, okay? And if you have a look at the first trajectory, it falls down to the earth pretty quickly. But as we fire the cannonball faster and faster, as the cannonball is falling towards the earth and curving in towards the earth is curving away from the cannonball. So as we fire the cannonball faster and faster, it spends longer and longer in free fall. So we get to this track and it eventually goes halfway around the Earth. And eventually, if we fire the cannonball fast enough, it goes on this track here and it just keeps on going. It keeps on going all the way around and then it comes right back to where it came from. And if you do this above the atmosphere and there's no air resistance, the cannonball's going to keep exactly the same speed and it's just going to keep going round and round indefinitely. And that's what an orbit is. So it might seem quite counterintuitive that it's not a case of like zero gravity or anything to do with gravity just being weaker. Gravity can be almost as strong as on the surface of the Earth, but we're constantly falling around the Earth. And that's what's going on with an orbit. So if we see in this picture here, this is a beautiful time-lapse photo of a SpaceX rocket being launched. Has anybody seen a rocket launch in real life? Okay, yeah, I haven't either. I would love to see a rocket launch one day. But if you look just at the beginning of a rocket launch, it just looks like it's just going straight up. And I think this is where a lot of the misconceptions with orbits and space in general comes from, that if you look at a rocket taking off, it looks like it's just going up and you can think, okay, well, to get to space, I've just got to go up and far enough away from the Earth that I'm not being affected by the gravity. But if you look a little longer, once the rocket starts to get above most of the Earth's atmosphere, it actually pitches over and it actually starts flying parallel to the horizon. And if you keep watching from where it's launched, it looks like the rocket is just falling over the horizon. And in a sense, that really is what it's doing. It's just entering an orbit. So it does need to get above the atmosphere so it doesn't worry about air resistance. But most of the energy of the rocket goes into accelerating the payload so it's fast enough that it can just reach that orbital speed and just keep orbiting around the Earth indefinitely. So getting into orbit, it's actually a question of going fast enough. It's not a question of going high enough. So we've got this question here. Let's have a think about how fast do we need to go in order to stay in orbit? And this is really where this combination of gravity and circular motion comes in. So we know when we have acceleration due to gravity, we know what that is, gm over r squared. And we know that in circular motion, whenever we have any kind of circular motion, our acceleration is v squared over r, so minus v squared over r. And if we want to be in a stable circular orbit, these two have to be equal. So our acceleration due to gravity has to equal that circular acceleration. So with a bit of algebra, we can work out what our orbital speed has to be. So give this question a go. We'll take a look at the results in just a moment. All right, let's take a look at the responses. Let's see what everybody thinks for this question. What's our orbital speed? Okay, no one going for C and D. Looks like people think it could be A or B. So we really need to just set these equal to each other, solve for V, and when we do that, what we get is option A over here. So V, our orbital speed, is equal to the square root of gm over r. So very well done, everybody, with this question. Now, this situation, I think, is where we often get a lot of misconceptions coming in with orbits. And especially if you're reading about this online, you might say, okay, well, you might see people saying, okay, gravity, and it's cancelled out by the centrifugal force because they think that that's like the centrifugal acceleration. But that's not what's going on. There's only one force involved in orbits, and that's the force of gravity. And in an orbit, that's equal to our circular acceleration. And that's where we get this speed from, okay? So do watch out for that misconception if you're revising orbits online or anything like that. So this is how fast we need to go in order to remain in orbit. So let's try an example. Let's put some values in here for the International Space Station. So we've got Newton's gravitational constant, we've got the mass of the Earth, and just remember with this radius, we've got the radius of the Earth, so where we all are now. Don't forget to add on this extra distance here. So this is the height that the International Space Station is above the atmosphere. So see what you get for the orbital velocity. We'll see how fast the International Space Station has to go to stay in orbit. All right, let's take a look. How fast do we have to go to stay in a circular orbit? Let's have a look. Okay, so people mainly think in B and C. Not so people going for A and D. So I thought when you put the values in, what we actually get here is option B. So I'm not sure why people are going for option C there. Is that what you get if you don't put in the extra distance, maybe? Okay, but yeah, so our orbital speed, 7.7 kilometers per second, okay? So very well done if you figured that one out, okay? What does everybody reckon to that? 7.7 kilometers per second. What do you reckon to that kind of speed? So it really is an unbelievably fast speed, okay? If you think about somewhere, how far away is some town? 7.7 kilometers away. So I don't know, you might be able to get to Durham or somewhere like that. Imagine traveling that distance in just 1 second, okay? So in order to stay in orbit, you really have to be traveling unbelievably fast, okay? So for the last kind of picture I'd like to share with you guys, I'd just like to share with you guys a really cool picture, one of my favorite pictures. Has anybody seen a movie of a rocket launching like this, something like that? Okay, so this is currently the heaviest lift rocket available. And it needs all of this power, all of this energy, not just to get the payload above the atmosphere, but the main thing that the rocket is doing, it's accelerating to those orbital speeds so that the payload is going to be circling fast enough that it can remain in orbit. So that's the secret to what's going on with orbits. And with that, that brings us to the end of the syllabus for the year. I hope you guys have all found it interesting, quite a lot of stuff to be thinking about. Please do let me know if you have any questions, if you're thinking about the exam, if you're thinking about what to revise. We've got a bit of time to be going over that kind of stuff. But I think for today, for this year, I don't know about you guys, I can't believe how quickly it's gone by. Like I said at the beginning, it seems like just a moment ago, we were in that first lecture way back in week 1 of the first semester. So I thank you guys all so much. I hope you've enjoyed with all the questions and stuff. And I hope you guys have a fantastic summer. But thanks, everybody. That's it for now.